Hi, do you suck at sampling distributions? You do? Well, that's good to hear because that's exactly what we're going to go over today. Welcome to AP Statistics Chapter 7 Review. That's Unit 5 if you're a chump and you followed the College 40 unit schedule instead of the textbook schedule, which is much better. We're going over sampling distributions, so let's get right into it. What is a sampling distribution? Before we do that, we need to define some key terms, right? So a parameter is data regarding a population. Say you're measuring average height in adult males. Your population is 150 million people. Let's say we end up estimating that the average height is 5'10". That is a parameter. The parameter in this case is the average height, and it's 5'10". So that's a parameter. That's what we use that term for. A statistic is data regarding a sample. In that 150 million adult males, you take a sample of 150 people, and it turns out in that sample, the average that you get is 6'1". So that would be data regarding a sample, and that's what we call a statistic. A proportion is a measurement regarding categorical data, which is measured as a percentage or decimal value. Um, you take a sample of 300 people, of which 65% like the color blue. That's a proportion. That's 65% or 0.65. That is a proportion. Mean is a measurement regarding quantitative data, which is the average of all values in a sample or population. Like we were talking about earlier, average adult male height, that would be a mean. Standard deviation, how far a data point typically is from the mean. Standard deviation in a sample of 150 people regarding average height of an adult male is 1 inch. That's a standard deviation. So, little chart that you might want to familiarize yourself with because these things are going to be good to know when you're writing an FRQ on the AP exam. Don't want to get stuck figuring out your symbols. So, proportion for the parameter, it's p or pi. I prefer using pi just because it fits the pattern of these Greek letters over here. Parameter for mean is mu. Parameter for standard deviation is lowercase sigma, and parameter symbol for population size is capital N. Now over on the statistics side, the proportion we call that p hat. Statistic for mean we call that x bar. Statistic symbol for standard deviation is s sub x or s. I prefer using s sub x. Ignore this down here. And for popular sample size for the statistics, it is lowercase n. So get used to those. It's good to know. Anyway, what is a sampling distribution? So, sampling distribution is a probability distribution showing the relative likelihood of sample statistics after taking many samples. That's a lot of big words. What does that mean? Well, basically, when you take a sample, you get some sort of measurement from that, right? That's what we call a statistic. Now you take another sample, you get a slightly different measurement. Another sample, you get a different measurement. And you take more and more and more samples and you stack them up on each other. And eventually you're going to get a distribution that shows um, the statistics that you get from all of those samples. So essentially, it's a sample of samples. So a true sampling distribution displays statistics from all possible samples of size n, but in most cases it's approximated. Because when you have samples of large size, your population distributions are going to have massive numbers because you're taking every possible combination from every possible sample of that size. And that gets to be really, really large, which is not possible in the real world most of the time. So, now why is this useful? Sampling distributions allow us to verify whether or not a claim about a population is reasonable and whether or not a sample was taken correctly. This is an example of a sampling distribution. Seems to be measuring a proportion of some sort down here, and you can see it centers on 0.23. The distribution is approximately normal, no left or right skew, no bimodal, anything like that. Um, you know, pretty standard. Now, sampling distributions, specifically for proportions, let's talk about that a little bit. Samples are always going to have some variability, and basically sampling distributions measure that variability. So repeated sampling will lead to the sample proportion centering on the true population proportion. This can be expressed with the formula mu sub p hat equals pi. This means the average of all your p hats is equal to the true population proportion. So, for example, you take a lot of different samples of people who uh, who have the favorite color blue. Let's say that's like, in one sample it's 13%, one sample it's 20%, another sample it's 17%. When you do that over and over and over and over again, you're going to get centered on the true population proportion, which is, let's say, 16.5%. So that's basically how that works. In order for this to be true, you must use an unbiased estimate to take your sample. That means you have to take a simple random sample. Can't use any bad sampling methods. You have to do it with a simple random sample, SRS. So if mu sub p hat is not equal to pi, then that means there's bias of some kind present, most likely. Now, mu sub p hat equals pi. This is the actual proportion, percent or decimal value, 16.5%, 50%, 65%, doesn't matter. It is a percent or decimal value. Mu sub p hat equals n times pi is the actual number in the sample. For example, if you have a sample with 100 people and 65% of them like the color blue, then that means that 65 people in the sample like the color blue. Using either one is fine, but you must be consistent with what you're using and make it clear which is which. For the record, I myself prefer mu sub p hat equals pi because it fits the pattern of working with proportions and percent decimal values. Whatever. Anyway, sampling distributions for proportions continued. Another important aspect of sampling distributions is their spread, the standard deviation. Wider spread means a larger standard deviation, which means a higher variability. And so the formula we use to calculate that is sigma sub p hat is equal to square root of pi times 1 minus pi over n. So basically, this means the square root of option A times option B over sample size square rooted. So for this calculation to be reliable, there's another condition. The sample size cannot exceed 10% of the population. If it does, then that means the factor of independence is lost, and this no longer becomes a reliable calculation. This can be displayed with this little inequality over here. Little n is less than or equal to 1/10 times large n, where this is the sample size, this is the population size, like we discussed earlier. Now, and it's under the square root. Because of this, higher sample sizes lead to reduced standard deviation, and outliers have a decreased effect. This is one of the many examples that you will see going forward, that a higher sample size is beneficial in so many different ways. This is just a little visual representation of what we just discussed. Higher sample size means that there's less spread, less variability. More of the samples are going to be centering on here because they're closer approximating the true population proportion rather than the samples that have smaller sample size. So let's see. As the sample size n increases, the sampling distribution increasingly approximates normality. So, however, a condition needs to be met to assume an approximately normal distribution. So it's only normal with the relevant mean and standard deviation if the sample size times the proportion is greater than or equal to 10, and the sample size times 1 minus the proportion is greater than or equal to 10. This is important, and it's called the large counts condition. You have to check this to do inference. You'll see that going in forward in the next chapters. So if this condition is not met, then the shape of the distribution is assumed to be unknown. That means you cannot use an area probability calculations using something like a normal CDF. So sampling distributions for proportions. In figure A, we have a high variability and a high bias. As you can see, it's not centering on the true population parameter, and it also has a pretty wide spread. In B, or sorry, down here, low variability and low bias. You can see there is not much spread, and it also centers pretty much on the true population value. And over here, there's a high variability and a low bias because it correctly centers here, but there is a large spread, which makes it a little bit harder to work with. And over here in figure D, there's a low spread but high bias. This is nowhere near the true population parameter, meaning the samples are clearly not being taken correctly, as we can most likely assume. Let's move on to sampling distributions for means. Sampling distributions for means follow the same principles as those for proportions. It's just going to use some different formulas. So average of sample means expressed using the following formula. Mu sub x bar equals population mu. So again, SRS needs to be used for this to be true. Basically, average of all your sample means is going to be equal to the true population mean. Excuse me. Sampling distributions for means continue. Standard deviation for means follows the same rules, but again has a slightly different formula. Sigma sub x bar equals population standard deviation over square root of n. Again, you need the 10% condition to be met for this to be true. And sampling distributions for means normality condition. To assume an approximately normal distribution for a sampling distribution regarding mean, a different condition needs to be met. This is not the large counts condition. You have an approximately normal sampling distribution with mu sub x bar and sigma sub x bar if your sample size n is greater than or equal to 30. This comes from something called the central limit theorem, which has a lot of different complicated components, but for the purposes of AP statistics and the AP statistics exam, this is the important thing you need to know. If the sample size is greater than or equal to 30, that means that the sampling distribution is assumed to be approximately normal, and you can use area calculations like normal CDF to approximate your values. So, this is a chart that basically sums up everything we discussed so far. You might want to pause the video here, write this down, screenshot, whatever you want. Yeah, essentially that's pretty much it for this chapter. Again, this chapter is not too complicated, but you really have to know this stuff well in order to move on to the real inference. That's going to happen in chapters 8, 9, 10, and 11. So, that's pretty much it.